In a swimming pool, a small circular island is divided into n sectors. These sectors are obtained by cutting our island, by segments through its center, in such a way that the angles between any two adjacent segments are equal. For example, in the illustration we have that n is equal to 6, that is, we have 6 sectors. Each sector is divided into 2 grids, its outer and inner grids. For each grid G, its neighboring grids are those grids which share a common boundary with G. For example, the neighbors of the following emphasized inner grid are the following emphasized grids. For another example, the neighbors of the following emphasized outer grid are the following grids. Initially, 4n+1 frogs jump into the island. For example, in our case, since n is equal to 6, the number of frogs will be equal to 25. It is difficult for the frogs to be quiet together, and hence, if there is a grid with at least 3 frogs, then some 3 frogs from this grid jump simultaneously into the 3 neighboring grids. For example, we see that in the emphasized grids, there are at least 3 frogs. Hence, at the first step, the movement of the frogs will be as in the illustration. Next, we see that in the emphasized grids, we have at least 3 frogs. Hence, in the second step, the movement of the frogs will be as follows. The main problem: prove that there exists a step S, such that for any step after S, the distribution of the frogs in the pool will be uniform. Where by uniform, we mean that the following condition is satisfied. For each grid G in the pool, either G contains at least 1 frog, or each of its neighboring grids contains at least 1 frog. For example, let us consider the case where n is equal to 3. Let us assume that we have the following extreme case, where initially all the frogs are found on 1 grid. Then, at the first few steps, the movement of the frogs will be as follows. Now, we are in a situation where the frogs are distributed uniformly on the grids. Let us check that they continue to be distributed uniformly in the following 3 next steps. As we will prove later, from here and after, the frogs will always be distributed uniformly. Let us now consider the case where n is equal to 4. We start with the following distribution of the frogs. Then, in the next few steps, the movement of the frogs will be as follows. As can be seen, at this point the distribution of the frogs is uniform. And similarly to the previous example, one can check that it will continue to be uniform at any step, from here and after. To prove that the frogs, eventually, distribute in the island, uniformly, we will introduce the following concepts. First, we call an event that there are 3 frogs in the same grid, which simultaneously jumping into 3 different neighboring grids, an eruption. Secondly, a grid is said to be in equilibrium if there are frogs in it, or there are frogs in all its 3 neighbors. Observe that the frogs will distribute uniformly, if, and only if there is some point, that each grid will be in equilibrium, and will continue to be so forever. Our first observation is that if a frog jumps into a grid G, then G will be in equilibrium from here, and for any step after. Indeed, if the grid G has no eruptions, then the frogs inside G will continue to be inside it, forever. Otherwise, if an eruption occurs in G, then each of its neighbors has at least 1 frog, and hence G is still in equilibrium. Then, G will continue to be in equilibrium, as long as there are no eruptions in its neighbors. On the other hand, if at some point, one of the neighbors of G has an eruption, then 1 frog jumps into G, and we return again to our initial case. Hence, in order to prove our main result, we just need to show that for each grid G, there will be some step, SG, which may depend on the grid G, such that, at SG, a frog jumps into G. The next concept that will be introduced is the clock number of an island with n sectors. First, we choose a sector and number it with 1. Then, we number the rest of the sectors by 2 through n, such that the resulting numbering will be clockwise. The clock number of the island, at step S, is the sum of squares of the labeling numbers of each sector, where the square value of each labeling is multiplied by the number of frogs in the corresponding sector. For example, in the illustration we have the case where n is equal to 8. Let us consider the following distribution of the frogs. Then, at sector 1, we have 3 frogs, at sector 2, we have 1 frog. At sector 3, there are no frogs. At sector 4, there are 5 frogs. At sector 5, there are 2 frogs. At sector 6, there are 3 frogs. At sector 7, there are no frogs. At sector 8, there are 2 frogs. Hence, the clock number at step S is equal to 373. We have the following 2 important observations with regard to the clock number of an island within sectors. First, the clock number is bounded from above. Indeed, the clock number reaches its maximum value when all the 4n plus 1 frogs are in the last sector n. And in this case, the value of the clock number is equal to n square, multiplied by 4n plus 1. Our second observation is that whenever eruption occurs in one of the sectors 1 through n-1, the value of the clock number is increased. Indeed, if eruption occurred in sector K, where K is between 2 and n-1, then the 3 frogs in sector K, which contributed 3k squared to the clock number, are now in sectors k-1, k, and k plus 1. Hence, now they will contribute k-1 square, plus k square, plus k plus 1 square, to the clock number. Hence, the total increased in the value of the clock number is exactly 2. Similarly, it can be shown that if eruption occurs at sector 1, then the clock number is increased by n squared plus 2. Lastly, our final main observation is that our process never ends. That is, there will always be a next step in our process. In other words, there will always be at least one grid G, with at least 3 frogs in it, so that an eruption will occur in the grid G. This is because, if 4n plus 1 frogs are distributed along 2n grids, then by the pigeonhole principle, there must be a grid with at least 3 frogs in it. We are ready now to prove our main result. As was explained previously, we only need to prove that for each grid G, there exists some step S, for which a frog jumps into G. We assume that there exists some grid G, with no frogs, and such that no frog will ever jump into G, and we need to obtain a contradiction. Let us denote by 1, the sector which contains the grid G, and starting from this sector, let us number the sectors clockwise from 1 to n. Let H be the other grid, in sector 1, which is different from the grid G. Observe that at no point, H can contain more than 2 frogs, since otherwise an eruption will happen in H, and hence, a frog will jump into the grid G. Since H contains at most 2 frogs, and G does not contain frogs at all, it follows that no eruption will ever occur at sector 1. However, eruptions must occur in the neighboring sector n. Indeed, otherwise, if at some point, eruptions occur only at sector 2, through n-1, then, since we have an infinite amount of steps, and since eruptions in these sectors only increase the clock number, it would follow that the clock number is unbounded, which is a contradiction since we showed that it is bounded from above. Hence, since eruptions will always occur at sector n, it follows that sector 1 will absorb frogs indefinitely, and will never erupt frogs. This implies that at some point, 1 frog will jump to grid G, or that grid H will contain at least 3 frogs. This is a contradiction to our initial assumptions, hence, some frog must jump eventually to grid G. Hence, our main assertion is true.